Hi everyone, we are continuing on, and we are now working with acceleration. So last time we worked on velocity versus time graphs, and during part of that we had to kind of discuss elements of the slope of a velocity versus time graph as being acceleration. And we also talked about average acceleration from a purely quantitative standpoint, as related to where we had done average velocity with position versus time graphs, right? But let's talk more about what is acceleration and also what are its concepts, what is its conceptual underpinnings, and how is it related to velocity, displacement, and everything else, okay? So if you haven't done the readings, please do so now. Do Coletta, OpenStax, or if you have Survey at Night, I've listed those chapters off too. And again, please start your homework, and we're going to be moving on, okay? So here are a set of questions. I really want you to think about this as a metacognitive exercise, and you're supposed to be investigating metacognition as you're supposed to be investigating your own beliefs and your own understandings of something, right? And I want you to ask yourself these questions and seriously think about this, okay? So the first question, is it possible for an object to be moving to the right, but actually accelerating to the right, okay? And if so, explain what you believe. And for number two, I want you to explain, is it possible for an object to be moving to the left, but accelerating to the right? And for number three, is it possible for an object to not be moving at all for an instant and yet still be accelerating at that moment? And also, is it possible for an object to have a constant speed but still be accelerating? And is it possible for an object to have a constant velocity and also be accelerating? So try to just briefly answer these questions and explain if it is possible and if it's not possible and how they would do it. And I put a number line here for you to try out. Okay, so please try this out. So hopefully you pause the video and try to do this, but let's think about it. Let's think about what is velocity. Now we know velocity, and we're going to try to answer question number one. We know velocity is a vector, okay? And what we had learned about last time, and all the, so let's go ahead. So we're going to go ahead and try to apply what we've learned. And we're going to use this position versus time graph, motion diagram scale to try to help us elaborate on some of these things. So let's try this first one. Is it possible to be moving to the right and accelerating to the right? Okay, so let's talk about that in terms of things that we've already done. So moving means velocity. So essentially, this goes into ultimately what is your overall questions? What is your understanding of what is acceleration? All right, and so we're gonna pivot back onto all of these questions, and I really want you to think about questions 1 and 2 and 3 when we go through these next sets of exercises. Okay. So let's talk about what is acceleration. Okay. So here we have a PowerPoint, and this is of a motion diagram, and this is of acceleration. Okay. And what do I mean by acceleration? Well, I don't like to use the term acceleration. I like to use the just basic terms, speed up and slow down, right? Typically, if we ever talk about acceleration, we talk about acceleration as speeding up. But really, when you're in a physics classroom, acceleration is a vector, and it's a vector separate from your velocity vector, okay? So here we go. We have a motion diagram, and if you notice, the dots are close together, so it's only moving this far in 1 second. And then a little bit later, it's going to be moving a little bit further in the period of the next second, and then a little bit further in the next second, and then finally at second therefore it's going to be moving a much larger displacement than it was from the 0 to 1 second. So 0 to 1 second, 1 to 2 seconds, 3 seconds, 4 seconds, right? So if we think about it, here we go. We have our little velocity vectors. And so the velocity vectors, if you notice, the displacement vectors, the green vectors, which are velocity as well as displacement vectors, are increasing in size over time, which means the object is speeding up over time. Well, what does velocity do? Well, if you think about it, if you take this initial velocity vector, so since an object is speeding up, what you could say is its initial velocity vector keeps getting longer and longer and longer over time. So what is happening is at each one of these points, there is something kind of dragging it and speeding it up in each part, right? So this arrow right here represents an acceleration. So for now, I think of acceleration like a force. So if you're walking along and somebody grabs you by your shirt and starts pulling you in the same direction, so I'm considering this acceleration vector a pull, you have an initial velocity vector, you're walking along at a constant velocity vector, and then I pull you. Well, if I give you just one little tug, now you're going to be going a little bit faster, right? And then if I continue to give you another tug right here, I pull you a little bit more, now you're going to be going a little bit faster. And then I tug you again, and now you're going to be going a little bit faster. So what acceleration really is, in my thoughts, is you have an initial velocity vector, and this separate vector, which is a push or a pull vector, is altering your velocity vector and then either increasing it or decreasing it in size, right? So here you have a velocity vector, and you add to that an acceleration vector, which alters your initial velocity vector right here. You have an initial velocity vector, you add to it an acceleration vector, and then you have a final velocity vector, right? Well, here you have velocity 0, 1, 0 seconds to 1 seconds. You add to that this acceleration vector, and here you have velocity vector 2. Okay? So you're adding that initial velocity vector here, and that is now this new velocity vector, velocity 1, 2. And then you're going to add velocity vector 1, 2 to another acceleration vector, and that will be velocity vector 2, 3. Well, then you add to that velocity vector 2, 3 to that acceleration vector, and now you have this final velocity vector 3, 4. Okay, so what an acceleration vector is it adds to or subtracts from an initial velocity vector. Okay, so that's what we're going to be using. So now we are back to our sheet now. So here is our note sheet. What you're doing here is if you have an acceleration vector, and I'm going to mark up this document, right? So basically, my real quick definition is an acceleration vector is it changes your velocity vector. Okay, so if we have an acceleration, if we start off with an initial velocity of 1 meter per second, okay, and it's pointed to the right, so it'd be positive 1 meter per second, and this is 1 second, 2 seconds, 3 seconds, 4 seconds, right? And let's say that the acceleration vector is also a positive 1 meter per second, but squared. It adds a velocity vector of 1 meter per second for every second. So from this 0 seconds to 1 second mark, that is your initial velocity vector of positive 1 meter per second. Okay. So I'm going to put 1 meter per second there. Now if I add this acceleration vector, and let's say it has the same type of acceleration every single time, and it's positive 1 meter per second squared, and I already put that here, then over the period of 1 second, from 0 seconds, so this goes from 0 seconds to 1 second, if I have an initial velocity of 1 meter per second, and now I'm going to add to that this, which happens over the period of 0 seconds to 1 second. So that's 1 second times 1 meter per second squared. Well, then that's going to be adding a velocity vector of 1 meter per second to our existing velocity vector of 1 meter per second. And now we're going to be moving to the right at 2 meters per second. Okay. Well, now you have a 2 meter per second velocity vector that you're going to now be adding a 1 meter per second squared over the period of now 2 to 3 seconds, which is 1 second, which is going to result to adding another velocity vector to that of 1 meter per second. And now you're going at 3 meters per second. That you're going to be adding a positive 1 meter per second squared over the period of 1 second, which happens to be 2 to 3 seconds. So now that's going to be plus 1 meter per second plus 3 meters per second. And now you're going to be traveling at 4 meters per second. Okay? And this is V01, V12, V23, and V34. 2 seconds, 3 seconds, and 4 seconds. So what ultimately is an acceleration is it comes from Newton's laws, which we're going to go over in forces, but it comes from an interaction where you have something pushing or pulling you, which then results in an acceleration vector, which is completely separate from your velocity vectors. So to go back, what you could say is, it is possible for me to have a velocity vector to the right of 1 meter per second. And then if you add to that an acceleration vector of positive 1 meter per second squared over the period of 1 second, 0 seconds to 1 second, what happens is then you have a resulting final velocity of 2 meters per second. Okay, so you add to this, these two things ends up becoming this. Okay, so really what this is speeding up. If you are moving to the right and you have an acceleration vector to the right, this is called speeding up. Okay? All right. Let's talk about the next one. So, what we have, is it possible to be moving to the left and accelerating to the right? Or another way of saying that is it possible to be moving to the right and accelerating to the left? Well, let's try it out. Let's say I'm moving to the left at -2 meters per second. And it doesn't matter what your position is, right? We've learned that velocity is separate from position. So let's say you're over here at the positive, this is 1, 2, 3, 4, positive 3 meters. Okay, so let's say you have a velocity vector to the left of, and this is an initial velocity vector of -2 meters over 1 second. So you started here, you ended here. So this is your 0 second mark, this is your 1 second mark. But let's say this, you have an acceleration vector to the right of a positive 1 meter per second. per second, okay, for that second. So basically this 1 meter, you're adding a velocity of positive 1 meter per second over the period of a second to this existing velocity vector of negative 2 meters per second, right? Well, what will happen is, and might have to change the location of this to illustrate this. Well, the result of this is this. If you are moving to the right and over the period of 1 second, your velocity is going to be changing here. So you're going to be adding a 1 meter per second velocity vector, a positive 1 meter per second velocity vector, to a negative 2 meter per second. What happens is at the end of that addition means now you're traveling at a positive at a negative 1 meter per second, right? Because your acceleration vector is now being added, is adding a positive velocity to your negative 2 meters per second. And what that is doing is it is slowing your object down. So this is going to be defined as slowing down. Okay. Well, whenever we can now make kind of a rule, whenever your velocity vector and acceleration vector are pointed in the same direction, so you have a positive velocity vector, positive acceleration vector, that is called speeding up. Whenever your velocity vector and acceleration vector are pointed in the same direction, in the negative direction in this case, that is called speeding up. However, whenever your velocity vector is pointed opposite your acceleration vector, that is called slowing down. That is called slowing down. So here we have another case. Is it possible for us to have a zero velocity vector, but also an acceleration vector? Is this possible? Well, let's try it out. Let's say you have a velocity, let's say you have an initial velocity of 0. So at 0 seconds you're not moving. Is it possible to add an acceleration vector? And I'm going to add an acceleration vector that is now to the left of negative 1 meter per second over another second. So from 1 second to 0 seconds. Well, initial velocity, again, we're going to be doing final velocity is equal to acceleration times time plus initial velocity. So you have an initial velocity of 0, and you're going to add to that a negative 1 meter per second over the period of 1 second. Well, then the resulting is going to be a negative 1 meter per second velocity vector. So what happens is now, after that first second, you're not moving, and then all of a sudden at the 1 second mark, now you begin moving. So what happens is now your 0 seconds and 1 seconds are on the same mark, and now you're going to be moving at negative 1 meter per second squared, and now you'll be at the 2 second mark. Then you're going to be adding that to the you're going to be adding a negative 1 meter per second velocity vector to your acceleration vector that is negative 1 meter per second over the period of 2 seconds minus 1 second, and now you're going to have an increased velocity vector. So yes, in fact, what you could say is this can also be called a turnaround. If you are moving to the right at a positive 1 meter per second, and then you come to a stop, and then you are now after that one point, now you're moving to the left at negative 1 second, what you could say is this whole time that you've been adding a negative 1 meter per second squared acceleration to this velocity, and then to that 0 velocity, and then you add it to it again, and now this object is turned around. Okay? So that's just some of the answers to those questions. And so this is a really good slide to talk about. Okay? Whenever your acceleration vector and velocity vector are pointed in the same direction, that is going to be called speeding up. So you have your velocity vector and acceleration that are both pointed in the positive direction. This will be speeding up, moving to the right. But here you have your velocity vector and acceleration vector pointed in the same direction to the left. And that will be speeding up to the left. However, here your velocity vector and acceleration vector are pointed in opposite directions. So in this case, you're going to be moving to the right, but you're going to be slowing down. Here, your velocity vector is to the left, but your acceleration vector is to the right. So this means you're going to be slowing down while moving to the left. Okay? And here's some other kind of things here where here's specific definitions of vectors related to that. But we've kind of already talked to them, but please read this if you have any questions. But what I'd like to do is get to some of the problem. Just to mention this real quick, this also applies for the vertical positions. If you are moving up, but you're accelerating down, that would mean that you are slowing down while moving up. And if you're moving down and accelerating down, that would be that you're speeding up as you're moving down. So this type of motion is really applied to up-down motion. And a lot of that we're going to get into when we're talking about objects thrown into the air. Okay? Now, here is a really cool slide, and I want you to just apply what you've learned. Okay? So I've put a little matrix here, and what you're going to do is I want you to categorize A, B, C, D, E, and F in terms of speeding up, slowing down, and constant velocity. After that, I want you to determine the direction of the green arrows. Those are the velocity vectors in terms of pointed to the right as positive or pointed to the left as negative. And from the concepts of speed up, slow down, and constant velocity that we've been learning, I want you to categorize the direction of the acceleration vectors as positive, negative, or zero acceleration. And I want you to do that in here. Okay? And after we've done that, we're going to use those categorizations to actually create motion equations. Okay? And so we're going to have a position versus time graph motion equation and also velocity versus time graph. So really by doing this, we're actually creating equations using vectors. So please try this right now. Okay, well hopefully you've tried each and every one of these. So let's take a look at A. So A is, if you notice the direction of A's arrows, they're all to the right. Okay, so this is the initial velocity vector. And if you notice, all of those vectors are pointed to the right. So what we could say is that A has a positive velocity. Okay, and so that A is to the right, and if you notice, the dots are close together here, which means it's going very slow. It's only moving a small distance over the period of a second. And the start point is the first dot. And then the final dot, it looks like it's almost traveling 4 times, maybe even 5 times. This is 2, 3, 4, 5 times. So this initial dot is going to, we'll just say, is analogous to a positive 1 meter per second, right? And then over here, it's adding 1 meter, so the acceleration vector is adding 1 meter per second. And I'm just kind of making up, I'm assuming that it's adding 1 meter per second every time, right? So this is 1, 2, 3 meter per second, 4 meter per second, and that's 5 meters per second, right? So it looks like the acceleration vector is actually lengthening these arrows, which means it is speeding up. And from our definition of speed up, that means your velocity vectors and acceleration vectors are pointed in the same direction. Therefore, if you have a positive velocity, you have to have a positive acceleration. Okay? So I just attach numbers to try to put this in a context, right? So I'm thinking that this length is about 1, and this looks about twice that length, and 3 times, and 4 times, and 5 times. And so I'm thinking that the acceleration vector is 1 meter per second as well. All right. What I want you to do is I want you to try that type of thinking for B, C, D, and F and see if that's kind of changed your thinking. So please pause the video and try to correct based off of what you just learned. Okay, we're back. So if you look at this, all of these arrows are also pointed to the right, but this looks like it's a +5 meter per second arrow. And in the end, it looks like it's going +1 meter per second, right? So those vectors, those velocity vectors are going to be positive as well, but that sounds like it's slowing down. If you're going 5 meters per second to the right, and then finally you're going 1 meter per second to the right, that's definitely slowing down. So that's SD, or just D, I should say. I should put these as U and D. So I'm going to be putting those as S. I'm going to just get rid of little S's in front. And that's because we're supposed to be categorizing these as U and D. Okay. All right. Well, if you are moving to the right, okay, and you're slowing down, that means you have to have a negative acceleration vector, right? Because something is decreasing these velocity vectors by 1 every time, right? Which means you have to be subtracting off from each one of those, okay? So that means your acceleration vector has to be negative. Okay, let's keep going, and we'll do your equations in a second. Let's just keep trying with this. Well, with C here, it looks like you start over here, so, and that vector is going to be pointed to the left, so that'll be -1 meter per second. And then in the end, it looks like it's going about 5 times that speed, which will be -5. So what that means is all of these vectors are going to be pointed to the left. So that'll be a negative velocity vector. And since they're increasing in number, even though they're getting more negative, that's still increasing in number. That just means traveling to your left, and your speedometer is going to be reading 1, 2, 3, 4, 5 miles an hour, or meters per second. So that means you're speeding up, which means you also have to have a negative acceleration vector, because the definition of speeding up is that your velocity vectors and acceleration vectors are pointing in the same direction. Okay, let's try over here. Let's try D. D looks like you start off at -5 meters per second, and then it looks like they're decreasing in size, which means that your speed, even though it's negative, it's going to be slowing down, which means you have to have a positive acceleration. So you have a -5 meters per second, and then now you have a -4 meters per second. Well, it seems like you added a +1 meter per second to this, which would mean that is going to be a positive acceleration vector that is being added to this negative velocity, these negative velocity vectors. And these are instantaneous velocity vectors. Okay? Cool. All right. Well, here you have a +1 meter per second, and they're all the same size, right? +1 meter per second. positive 1 meter per second. Well, that means you're adding velocity vectors to each one of these. So that means you have the same size velocity vectors that are all to the right. Which means if you add an acceleration vector, you have an initial velocity of positive 1, and your final velocity is positive 1. That means you're adding a 0 acceleration vector to that, which means you have a constant velocity, which means your acceleration is 0 here. Because if you have a positive 1 and a positive 1, the only way to get that difference, that is just 0 as a difference. So that means your acceleration is 0. And the antithesis is true for this. If you're moving to the left at a constant velocity, so you're moving to the left at a constant velocity, then the same thing is happening. You're just adding a 0. There's 0 difference between your initial velocity vector and the 0 initial negative velocity vector and the final velocity vector right here. So nothing has changed. Okay. Okay. Well, hopefully it was kind of cool for you, but let's take it a step further. Here's how you're going to be using these. We've actually, by analyzing an object's motion on a motion diagram using vectors, well, now we've actually created equations, right? So for this first one, we're saying this, that we have a positive velocity and a positive acceleration. That means you have a positive velocity and you have a positive acceleration. In a position versus time graph, and we'll get into this in a little bit, it's going to be a curvilinear. So we'd learned that, I mean, just imagine this isn't here. There was a line now on a position versus time graph, a straight line. Well, now, by having a changing slope, by our slope being able to change, well, now we have to add another component, which is the acceleration component. Okay, so A is saying this, I have a positive velocity vector and positive acceleration vector, so we're supposed to put positives here for each one of those. If your velocity is positive on a position versus time graph, if your initial velocity is positive on an acceleration versus time graph, then your velocity, okay, let me say that again. If your initial velocity vector is positive on a position versus time graph, then your initial velocity will be positive on a velocity versus time graph. And same thing for the acceleration. Okay, if this is positive, this has to be positive. If your acceleration is positive, then this component has to also be positive. You can't have a positive here and a negative here. So these two have to work together. Okay. All right. Well, we've done part A. Part B's equation would look like this. Part B's equation would look like this. I have a positive initial velocity vector, right? But I have a negative acceleration vector. Okay, so that means that I'm going to be, while I'll be moving to the right at this instant, I will be accelerating to the left. I will have an acceleration vector to the left, and that will mean I'm slowing down. So that's what B is. B is this part. So we've created an equation for B. Let's try C. Well, C is this. I have a negative velocity vector, and I have a negative acceleration vector. So here's the prediction equations for a position versus time graph and a velocity versus time graph for part C. Pretty cool. Let's try D. Well, D, I'm going to have also a negative initial velocity vectors, right? However, I'm going to have a positive acceleration because those velocity vectors are getting shorter over time. Okay? And so this is the prediction equations for position versus time and velocity versus time for D. All right, let's try E. Well, E, we're going to have a positive velocity vector in those two cases, but a 0 acceleration vector. Okay, so this is a linear equation on a position versus time graph. And a velocity versus time graph, it would be a straight horizontal line, just like we did at the beginning of this. So it would look something like this. It would actually look like C for a velocity versus time graph with a positive velocities. Okay, and let's do F. F, we would have a negative initial velocity, but also, again, no acceleration component to that. So that would be 0. It would just be these two things. It's weird, the final velocity is equal to the initial velocity, which kind of makes sense because that's what constant velocity means. There is no accelerated component. So on a velocity versus time graph, a negative velocity vector would look like graph B right here. Okay? All right. What I want to do now is let's move you on to, let's do some problems, okay? So how are these equations related directly to here? So basically on motion diagrams, the curve fits for a position versus time graph would be associated as such, which is what we just did. So I just wanted to reiterate our exercise that we just did. And so graph A is speeding up in the positive direction, so it's going to have a positive velocity and a positive acceleration. Graph B is going to be slowing down while moving in the positive x direction, so it's going to have a positive velocity and a negative acceleration vector. Diagram C is speeding up while moving to the left, so you're going to have a leftward velocity vector and also a leftward acceleration vector. Graph D is going to be slowing down while moving to the left, so it's got a negative initial velocity vector but a positive acceleration vector. Graphs E and F are both going to be constant velocities, but E is going to be to the right, so it's going to have a positive velocity vector, while E is to the left, so it's going to have a negative velocity vector. And these go with their counterparts for the velocity versus time graph. Okay, so notice that this initial velocity refers to this initial line right here. So that initial line is positive, okay, but notice that they're increasing in size, so that means it's accelerating or speeding up. Here, it has an initial velocity vector that is positive, but they're getting smaller over time, so that means it's slowing down, and the definition of slowing down is your velocity vector and acceleration vector are in opposite directions, so positive velocity, negative acceleration. And here we go, C, you're speeding up while moving to the left, so that means your negative acceleration vectors are going to be adding to this negative initial velocity vector and increasing its size each and every time. And this is the opposite here. Here you're moving to the left, but your acceleration vector is, so you have a negative velocity vector, but your acceleration vector is positive, so it's taking away from each one of those negative velocity vectors. Okay. E and F, again, are constant velocities, so they're just going to be pointed to the right in the same size every time, or pointed to the left in the same size every time. Okay? So I hope you learned a lot, and we're going to be moving on to applying these cases. So we're going to be moving on to applying these cases, and how do you do vector addition to create acceleration equations, okay? And so this is going to be kind of adding to what we just learned. Okay? I hope you had a good time.